Okay, let me talk about conditional expectation. So we need to start out with what's called a probability triple. So that's a sample space, omega, and a family of events that we can measure, and then a probability that we can associate to every event in this family. So this is known as the probability triple. Okay, so that's sort of the basic setup for probability. And then we can look at random variables, and these are functions defined on the sample space that give you numbers. You should think of these as measurements. Okay, so, and for simplicity, I'm going to do everything in the discrete case. So this is a discrete random variable. Okay, so let's take, for reference, let's fix an event B that we can actually measure, so it's in F. And for, to avoid problems, I'm going to assume that it's a non-trivial event that has some probability, a non-zero probability of happening. Now, given that, I can then condition my variable x to the event b. And how does that work? Well, it's the same formula as for expectation. So you look at the places where x is equal to some little x, multiplied with its probability. This has to be done, taken in all possibilities. But the difference is that now we're going to condition here on b. Okay, that's the only difference in the formula for expectation. In terms of integrals, the integral approach, it would be like if we were to integrate the variable the variable x on the event b, and then sort of take the average. So divide by the measure of b. Now, you just draw this to stay within the bounds. Suppose you have a partition, right? So suppose you have some number of events b1 through bn, and these form a partition of omega. Well, you should, in the back of your mind, you should think of a way of tiling omega up into pieces. Okay, so this is b1, etc. And you could think of this some states, right? And this being a geographical map. Then you can condition on the partition, and you can write, say that you want to compute the expectation of x. You can compute the conditional expectation in each case, and then sort of sum them up, right? So it goes like this. You go from 1 to n, you do the expectation of x given bj, and then you multiply by the probability of bj. Okay, in terms of this definition, it's clear that when you multiply by bj, you get the integral over bj, and so you're integrating over each one of them, and when you sum them, you get the total integral. So using this formula, it becomes evident that this formula holds. So let me give you an example to see this in action. So let's say that you repeatedly toss a coin, say a bias coin, and this coin has a certain probability p of heads and 1 minus p of being tail. So, you know, the typical event will look like this: heads, heads, tails, etc., or tails, tails, heads, and tails, etc. Right? These are the typical outcomes. Now, I'm interested in the length of the initial run, so I'm going to call this L here, and and the initial run here is so the length of the initial run. So L, length of initial run. Okay, and then let's say that we want to compute the expectation of L. Okay. Well, we can do that by conditioning on some mutually exclusive events. Let's condition on the outcome of the first toss. So I'm going to condition on x1 being h. The probability of that event is p, plus the condition on x1 being tail, and the probability of that event is 1 minus p. Okay, so that's, I'm using this formula here. I'm partitioning omega with heads or tail, basically, and then I'm doing this. So, but now let's put ourselves in this situation. In this situation, the first toss was head, right? And then you were basically waiting for the first t. But that's the geometric distribution, right? So how long should you wait for the first t here? Well, you know what the probability of t is. The probability of t is 1 minus p. So how long should you wait? 1 over 1 minus p, right? So that's exactly what you get. 1 over 1 minus p times p for that. Plus, now here, the first toss was tail, and now we're waiting for the first head. And the first head comes in 1 over p. Right? This is the expectation of the geometric distribution. And so now we have a formula in terms of p of the length of the initial run. Okay, let me shift gear a little bit and introduce another random variable. So let me call y another discrete random variable. And discrete random variables are great at creating partitions, right? So this gives rise to a partition. So for instance, let's assume that that y takes values in 0, 1, up to n. It's a discrete random variable. We can always assume something like that if it's finite range, let's say. Then we can define a partition by letting bk, the tiles, I call these the tiles of the partition, we can let that be the level set, right? All the outcomes that have measurement y equal to k. And it's a partition because everybody has a certain value of y, so it's in one of these tiles. And you can be in both, in two tiles, right? Because y is equal to k, it cannot be equal to something else on that tile. So it's a partition, and this allows us to sort of condition our original random variable x on y by conditioning on this partition. And in fact, we do something a little strange. We get a third random variable, so you're going to let z be a new random variable, which is going to equal the conditional expectation of x on the tile y equal k whenever you are on that tile, so on y equal k. So this function, this random variable z is actually a function of y. Right? So it's completely dependent on y. It's a function of y. But it's actually, in a sense, the best function of y that more closely approximates x. So the language of projections here is very useful. So you should think of a plane where, you know, all the functions of y live in this plane. Then you have x, you think of x as a vector. And then you sort of project down onto that plane, you know, orthogonally. And that projection is z. Okay, this is, and the notation for z is, we write it as conditional expectation of x onto y. So this notation, one needs to get used to it, because, you know, you would think that this is a number, but it's not a number. It's a random variable. Okay, and it's this random variable right here. It's the projection of x onto the space of functions of y. Okay, so this is a tool that has amazing power and lots of properties. Let me just describe one property, the so-called averaging property. And the averaging property is basically a reinterpretation of this formula right here that we talked about earlier, the conditioning. Okay, so the averaging property says the following. It says that if you take the expectation of this random variable z, namely of the conditional expectation of x onto y, then that's the same as taking the expectation of x. Right? So you should think of this ex as being this ex, this expectation as being this sum weighted by, and then these are the values of z. Okay, so that's the parallel. And let me just give you an example instead of proving this. I'm going to just do an example. Let's suppose that we repeatedly roll a die, a fair die. So repeatedly roll a fair die until 6, the number 6 appears. And then you stop. Okay? Now, first of all, we will define y to be the random variable that gives us the number of rolls. Okay? And we already know that this is going to be a geometric random variable, but that's not the point right now. And let me let x be the number of ones that we see in the process. So we repeatedly roll a die until 6 appears, and then count the number of ones that we saw. Okay, so let's compute the expectation of x given y. Well, what are the possible values of y? Well, y could be 1, 2, 3, etc. Right? It's a geometric distribution, so it could be any of these. And let's just fix one of them. So let's compute x of y when y is little y. Well, if you know the length, right, if you know how many rolls you had to do before getting a 6, then you know that in this y minus 1 rows, you never had a 6, right? So you never had a 6, meaning you had a choice of 5 different numbers. And you want to know how many times 1 appeared, right? Well, 1 has a 1/5 chance of appearing. And so, because of the binomial distribution, this is going to be y minus 1 over 5. Okay? And so that means that we can now write z, this conditional expectation, as just y minus 1 over 5. Right, so you see, when I was saying earlier that z is a function of y, well, here is an example. Z in this case is y minus 1 over 5. It's a function of y. But it's not just any function of y, it's the best function of y that tries to approximate x. So that's the intuition. And let me try to verify the averaging property, right? So let's take, so then we can now compute the expected number of ones that we see in the process, right, ex, by taking the expectation of this. Okay, so the expectation of y minus 1 over 5. But y was a geometric distribution, right? You're repeating and rolling until you get a 6. And a 6 has 1/6 chance of appearing, so you expect to roll 6 times. So you get 6 minus 1 over 5, which is 1. So that means that you expect to see 1 instance of the number 1 in the process.